Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 33rd video lecture, and we're starting Chapter 8 today. Let me write up what we're concerned with. Really, we're concerned with special functions in this chapter, and there will be functions that can be represented by power series. And so, here's some comments to start us off. We will concern ourselves initially, so this is for Chapter 8, with real value functions that have power series representations. That is, we're looking at f of x's that are equal to the sum as n runs from 0 to infinity of c sub n of x raised to the n, or more generally, f of x equal to the sum as n runs from 0 to infinity of c sub n x minus a raised to the n, where x and c sub n are real numbers. As a definition, a function which has a power series representation is called an analytic function. Okay, as a comment, because we are concentrating on real analytic functions, there will be an interval of convergence as opposed to a circle of convergence for complex value functions. That are analytic. as a theorem, suppose the series the sum as n runs from 0 to infinity of c sub n x sub n converges for x less than some number r, and we define f of x to be equal to that series for each x in the radius of convergence. Then the sequence of partial sums converge uniformly on this closed interval from r minus epsilon up to, should be minus r plus epsilon, I meant that, up to r minus epsilon, no matter which epsilon bigger than 0, less than r is chosen. Not only that, but the function f of x is, it's going to have some nice properties. Is continuous and differentiable n minus r to r, and the derivative of f is the sum as n runs from 1 to infinity of n times c sub n x to the n minus 1. And that's true for all x's with absolute value of x being less than r. And that's what we'd expect the derivative to be if we took the derivative term by term of the quantities that we're adding together to get f of x. Here's the proof. We let epsilon be greater than 0 be given. Okay. For the absolute value of x being less than r minus epsilon, we have that the absolute values of c sub n times x sub n is equal to the absolute value of c sub n times the absolute value of x sub n. Which is less than or equal to the absolute value of c sub n times r minus epsilon raised to n. Here, this absolute value of x to the n is the same thing as the absolute value of x all raised to the n. This type of inequality, which we can say is less than the absolute value of c sub n times r minus epsilon raised to the n. Now, note, x equal to r minus epsilon is in the radius of convergence. Of the sum of C sub n x sub n running from 0 to infinity. Consider the sum as n goes from 0 to infinity of C sub n times r minus epsilon raised to n. And then applying the root test, to this series, okay, we have a lim sup, n goes to infinity, of the nth root of C sub n r minus epsilon raised to n. And we're going to take the absolute value of that equals to the lim sup, as n goes to infinity, of the nth root of the absolute value of C sub n times r minus epsilon raised to the n, which is the same thing as r minus epsilon times the lim sup as n goes to infinity of the nth root of C sub n, that's the value of C sub n, okay, and then this is equal to r minus epsilon times 1 over r, where that 1 over r is the alpha which is associated to E, which we know is less than 1, because this is something smaller than r, over something, it is r, over r. And so that's less than 1. Okay. So, what we get is that the sum as n runs from 0 to infinity of C sub n r minus epsilon raised to n, that converges. What this essentially says, this work, all right, here. What this did was this shows that every power series converges absolutely in its interval of convergence. that's something we have. Now, since that's what value C sub n x of n is less than or equal to C sub n r minus epsilon raised to the n, and the series of C sub n times r minus epsilon raised to the n converges, then by a previous theorem, the power series converges uniformly for x being less than or equal to r minus epsilon. Less than or equal to. That is, the sum as n runs from 0 to infinity converges uniformly on minus r plus epsilon up to r minus epsilon. Okay, note that the limit as n goes to infinity of the nth root of n, which we've done this before, I believe. The limit as n goes to infinity of n to the 1 over n. And then we consider the limit as n goes to infinity of ln of n raised to the 1 over n, which equals to the limit as n goes to infinity 1 over n times ln of n, which we can look at as the limit as n goes to infinity of ln of n over n, where the bottom's infinity, so we'll take the derivative of the top and the bottom, we'll put the n, we'll get 1 over, well, it's a limit. Use the L'Hopital's rule, limit as n goes to infinity of 1 over n over 1, which equals to 0. So this says that the limit as n goes to infinity of the nth root of n is equal to e to the 0, which is 1. So that gives us that the lim sup as n goes to infinity of the nth root of n times the absolute value of c sub n is going to be equal to the lim sup as n goes to infinity of absolute value of c sub n, and thus f of x equaling the sum as n runs from 0 to infinity of c sub n x sub n, and the power series as n runs from 1 to infinity of n times c sub n x raised to n minus 1 have the same radius of convergence. Okay, since the sum as n runs from 1 to infinity of n times c sub n x to the n minus 1 is a power series, it converges uniformly on minus r plus epsilon up to r minus epsilon. Note, if we look at f sub n equal to the sum as k runs from 0 to n of c sub k x to the k, this converges pointwise to 0 when x equals to 0. And I'll write down x of naught equals to 0. This x of naught is matching the information that we have here for these f sub n's to a theorem that I'm going to be using, just like we're going to be using just a second. And f sub n is differentiable on minus r plus epsilon to r minus epsilon. This is true because this is a finite sum here. So each one of them is differentiable. Just apply the sum rule and the power rule here. Differentiability. Okay. So what we have is, since the f sub n's converge uniformly to f on minus r plus epsilon, minus r plus epsilon, and then to r minus epsilon, we have that f prime of x will be equal to the limit as n goes to infinity of the derivatives of the f sub n's, which will equal to the sum as k runs from 1 to infinity of c sub k times k x to the k minus 1, and that is for all x's with whose absolute value is less than r minus epsilon. Now, let x be a real number such that the absolute value of x is less than r. Then we can find an epsilon greater than 0 such that the absolute value of x is less than r minus epsilon. So that says f prime of x is equal to the sum as n runs from 1 to infinity of n times c sub n x sub n, and that's true for all x with absolute value of x less than r. This should have been to the n minus 1. Okay, as a corollary, so that is this thing. As a corollary, suppose the series the sum as n runs from 0 to infinity of c sub n x sub n converges for x less than r and define f of x being equal to the sum as n runs from 1 to infinity of c sub n x to the n for x being less than or equal to r inside x values. Then f has all derivatives n minus r to r, which are given by the kth derivative at x is equal to the sum as n runs from k to infinity of n times n minus 1 all the way down to being multiplied by n minus k plus 1, and then c sub n x raised to the n minus k. And I'll say which is equal to, so another form of that expression is n runs from, summation is n runs from k to infinity of n factorial over n minus k factorial c sub n x to the n minus k. Okay. And in particular, if you look at the kth derivative evaluated at 0, that's going to be equal to k factorial times c to the k for k equaling 0, 1, 2, forever. And the proof is by induction. That's the way I'm going to do it. So we're going to let the sum as n runs from 0 to infinity of c sub n x sub n converge for x less than r and define f of x to be equal to the sum as n runs from 0 to infinity of c sub n x to the n, again for all x values so that their absolute value is less than r. show f has all derivatives n minus r up to r with the derivatives, the kth derivative, value of x equal to this sum as n runs from k to infinity of n factorial over n minus k factorial c sub n x to the n minus k, and the kth derivative evaluated to 0 is equal to k factorial times c sub k. And that's supposed to be true for k equaling 0, 1, 2, 3, forever. All right, let's start off, first of all, since it's by induction, let's start off with k equaling, note for k equaling 0. Then the 0th derivative evaluated x, well, that's just f of x. And so that's equal to the sum as n runs from 0 to infinity c sub n x sub n, which indeed is the sum as n runs from 0 to infinity of n factorial over n minus 0 factorial, which is n factorial. That's just 1. C sub n x to the n minus 0. So that formula is correct. What we're trying to show is correct for 0. And f of 0, well, f of 0, we're going to get 0 every time except when n is equal to 0, so the first term. And so we're just going to get c sub 0. Here we're taking 0 to 0 to be equal to 1. So the statement is true for k equal to 0. Okay. When k is equal to 1, the previous theorem gives, that's why it's correct, f prime of x is equal to the sum as n runs from 1 to infinity of n times c sub n x to the n minus 1, which is the same thing as the sum as n runs from 1 to infinity of n factorial over n minus 1 factorial, because all that will be left when you have cancellation here will just be n, c sub n x to the n minus 1. And if you look at f prime evaluated to 0, here we're going to have 0 raised to powers. And the only time that is at 0 is when the power is 0. And that happens when n is equal to 1. So we have n, that's 1, when n is equal to 1, times c sub 1. And that is 1 factorial times c sub 1. Okay. So the statement is true when k equals to 1. Okay. Now we're going to assume the statement is true. When k
k is equal to some fixed number, let's say j, and we want to show the statement is true when k is equal to j plus 1. So what we're assuming is that f, the jth derivative, evaluated x, is equal to the sum is n runs from j to infinity of n factorial from n minus j factorial, c sub n, x sub n minus j, and the jth derivative evaluated to 0 is equal to j factorial times c sub j. Now, if we letting maybe u equal to j minus 1, or I should say n minus j. Then we have that the jth derivative is equal to this sum. So I'm talking about this sum. I'm going to have it u, that's a u, goes from, well, n goes from, starts off its lowest as j minus j is 0. So u goes from 0 to infinity. N will be u plus j. So it's u plus j factorial over u factorial. C, and then n is u plus j, x to the u. That's what we have. So by the previous theorem, the derivative of this, that would be the j plus 1 derivative, evaluated at x is equal to the sum as u runs from 1 to infinity of u plus j factorial over u factorial times u times c to the u plus j times x to the u minus 1. Okay, all right. Now, letting n equal to u plus j, we have f raised to the j plus 1 derivative of f evaluated x is equal to the sum as u will run from, I'm sorry, not u, but n, will run from j plus 1 up to infinity of n factorial over n minus j factorial, c sub n times n minus j times x to the n minus j minus 1. Give me just a second. Well, that's right. Okay. And that equals to the sum as n runs from j plus 1 up to infinity of n factorial over n minus j minus 1 factorial, where the n minus j and the n minus j factorial will cancel out with n minus j here, just leaving n minus j minus 1 factorial. And then this would be c sub n x to the n minus j plus 1. And that's what we wanted to show. And if you look at the the j plus 1 derivative evaluated at 0, the only term that isn't going to be 0 is the first term. So this will be j plus 1 factorial over, here, this will be j plus 1 minus j minus 1. And so we get 0 factorial. This would be c sub j plus 1 x to the 0, which is going to be 1 here. Okay, so we don't have 0, so that's going to be 1. Which equals to j plus 1 factorial c sub j plus 1. That's what we wanted to show. So that concludes this proof. Okay, next theorem, do the apple. Here's what it says. To suppose the sum as n, runs from 0 to infinity of c sub n converges. Put alpha of x equaling to the sum of c sub n x to the n, as n runs from 0 to infinity, and that for minus 1 less than x less than 1, then the limit as x goes to 1 of f of x equals to the sum as n goes from 0 to infinity of c sub n's. Proof's a little bit lengthy. We're going to get through with it here. So, in this video lecture, proof. Suppose the sum as n runs from 0 to infinity of c sub n converges. Consider the power series sum as n runs from 0 to infinity of c sub n x to the n. Now we let alpha be equal to the lim sup as n goes to infinity of the nth root of the absolute values of the c sub n's. And r equal to 1 over alpha, where r is equal to infinity if alpha equals to 0 and And R equals to 0 if alpha equals to infinity. By a previous theorem, we know this power series converges if the absolute value of x is less than r, and diverges if the absolute value of x is bigger than r. Since the sum is n run from 0 to infinity of c sub n times 1 to the n, this is our function evaluated at 1, equals to the sum as n goes from 0 to infinity of c sub n, which converges, then 1 cannot be bigger than r. So r has to be bigger than or equal to 1. So that means that this sum, as n runs from 0 to infinity, of c sub n x to the n converges for the absolute value of x being less than 1. Thus, f of x equals the sum as n runs from 0 to infinity of c sub n x to the n defines a function on -1 to 1. Now, we're going to let the s sub n be equal to c sub 0 plus c sub 1 plus c sub 2 plus all the way up to c sub n for n 1, 2, 3, forever, and s sub -1 be equal to 0. Thus, if you look at s sub n minus s sub n minus 1, that's going to be equal to c sub 0 plus c sub 1 plus all the way up to c sub n minus c sub 0 plus c sub 1 plus all the way up to c sub n minus 1, which equals to c sub n, and that's true if n is bigger than or equal to 1. When n equals to 0, s sub 0 minus s sub minus 1 is equal to c sub 0. So what we get is s sub n minus s sub n minus 1 equals to c sub n. And that's true for all n equal to 0, 1, 2, forever. Thus, the sum is n runs from 0 to m of c sub n x sub x raised to m, is really the sum as n, this should be n, the sum as n runs from 0 to m of s of n minus s of n minus 1 times x of n, which equals to the sum as n runs from 0 to m of s of n x of n minus the sum as n runs from 0 to m of s of n minus 1 times x of n, which equals to the sum as n runs from 0 to m minus 1 of f, let me write that. N runs from 0 to n minus 1 of s of n, x of n, minus the same sum here, plus the one term missing from over there is s of m, x to the m. Now, here, we'll say this equals, and it's really because since s of minus 1 equals to 0, this is equal to the sum as n runs from 0 to m minus 1, s of n, x of n, so I hadn't changed that, minus, here's where we get that 0 term, so I might as well say the n runs from 1 to m of s of n minus 1, x sub n, plus the s of m, x of m. X of m. Okay, now letting u equal to n minus 1 and the second summation, that's what I'm doing. We get the sum as n runs from 0 to m minus 1, s of n, x of n, minus the sum is, here we're letting u goes from 0 to m minus 1. It was s sub u, x sub u plus 1, plus that last term, s of m, x raised to the m, which will be equal to the sum as n runs from 0 to m minus 1, s of n, x of n, minus, here we'll take out an x, doesn't have just one factor of x, sum as u runs from 0 to m minus 1, s of u, x to the u, plus s of m, x of m, and now letting u equal to n, just to translate everything in terms of n's again. N runs from 0 to n minus 1 of s of n, x of n, minus x times the sum as n runs from 0 to m minus 1, s of n, x to the n, plus s of m, x to the m. And here, this is the same thing as 1 minus x. I'm going to factor out this summation. S of n, x of n here, plus this one last term. Okay. Let's note that since the s of m is really the sum as k runs from m, 0 to m, I should say, of the c sub k's and the sum of the C sub k's, k runs from 0 to infinity, converges. So the S sub m are partial sums here. Then the sequence of partial sums converges to a number, say S, and this is, so for the absolute value of x being less than 1, alpha of x is equal to the limit as m goes to infinity of the sum as n runs from 0 to m of the C sub n's, which we've shown the sum is the same thing as the limit as m goes to infinity of 1 minus x times the sum as n runs from 0 to m minus 1 of s of n x to the n plus, there's one more term, that s of m x to the m, but this part goes to 0. So this is equal to 1 minus x times the sum as n goes from 0 to infinity of s of n x to the n. Okay, why that last term, s of n x to the n, goes to 0? This guy goes to x, and x to the m goes to 0 when we're talking about x values whose absolute value is less than 1. Okay. Now we let epsilon be greater than 0 be given. We want to show that the limit as x goes to 1 of f of x is equal to this sum as n runs from 0 to infinity of the C sub n. So that's what we wanted to show. Okay, so to do that, we want a delta bigger than 0 such that for all x element of minus 1 to 1 with the absolute value of x minus 1 less than delta. I'm just using the definition of limit here. That f of x minus this sum is n runs from 0 to infinity of c sub k, which is the number, c sub n, is less than epsilon. Since the limit as n goes to infinity of s of n equals to s, we choose n such that for all n bigger than or equal to big N, s minus s of n will be less than epsilon over 2. Since 1 minus x times the sum as n runs from 0 to infinity of x to the n equals to 1 minus x, this is the geometric series, over 1 minus x, and that's true for all x n minus 1 to 1, then s times 1 minus x times the sum as n runs from 0 to infinity of x of n really equals to s. Okay? And that's true for the x's in between minus 1 to 1. Thus we have The absolute value of f of x minus s is equal to the absolute value of 1 minus x times the sum as n runs from 0 to infinity of s of n, x of n, minus s times 1 minus x times the sum as n runs from 0 to infinity of x. This part is 1, or say it's s, which is equal to the absolute value of 1 minus x. We factor that out of both places. The sum as n times the sum as n runs from 0 to infinity of s of n, x of n, minus the sum as n runs from 0. This should be x to the n here. I made a mistake. N runs from 0 to infinity of x to the n, which we can rewrite as the absolute value of 1 minus x. We combine these two sums to be one sum as n runs from 0 to infinity of s of n, x of n. Hold it, I forgot an s here. So let's pull this s inside. Huh? Got that s. So this is s of n minus s times x of n. And then, using the triangle inequality, first of all, we take the absolute value of this guy and the absolute value of the sum. The absolute value of 1 minus x, for x is in between minus 1 and 1. 1 minus x will be positive, so this is just 1 minus x. And then the absolute value of the sum is less than or equal to the sum of the absolute values. And that's what we get. Which equals to 1 minus x, the sum as n runs from 0 to this big N that we have, of the s of n's minus s times the absolute value of x raised to the n plus this 1 minus x times the sum as n runs from big N plus 1 to infinity of the absolute value of s of n minus x times x to the n, which is less than 1 minus x times the sum as n runs from 0 to infinity, s of n minus s, x to the n. So that's the values, and then plus this guy, we had the less than epsilon over 2, that's the constant I can replace this with, and then 1 minus x times the sum of the x of n's running from n plus, big N plus 1 to infinity. Okay, we're getting close to being done. Okay, that last sum is going to be less than the sum running from 0 to infinity, and that time the 1 over x was just 1. So this is going to be less than 1 minus x, write down the first sum, plus epsilon over 2. Okay? Okay, if we let m equal to the maximum of the s of 0 minus s, s of 1 minus s, all the way up to s of big N minus s. Okay. Then, and let delta be equal to epsilon over 2 times m times n at the bottom. Then, for all x element from minus 1 to 1, we have that the f sub x minus s inside absolute values is less than this 1 minus x right here, times the sum. Okay, here I'm going to replace this guy with m, absolute value of x raised to the n plus epsilon over 2. Okay. And and this n's running from 0 to big N. I pull out the m. 1 minus x. Let's make it less than. Pull out the 1 over x. Pull out the m. Here, this is the sum. It's equal to. Sum is n runs from 0 to n, so that's the value of x sub n plus epsilon over 2. We're almost done. Which is going to be less than or equal to 1 minus x m. Now the norm of x is going to be less than 1, and so that's going to be less than 1 added up n times. So I'll say n plus epsilon over 2, which is less than. The delta here is epsilon over the 1 minus x is going to be less than epsilon over 2 times mn times n plus epsilon over 2, which equals to epsilon. And that concludes the proof. Thank you very much for your time and patience. That concludes lecture 33.